All right, so as I said, we went through stages of the cell cycle, compared rates of division, different types of cells. We might review that again once we're done with this part of the notes, but for the sake of recording it, we're just going to cover the surface area to volume stuff and go from there. So we're really working on this, identifying the factors that limit cell size, that last objective, right? Cells can only be so big before they need to divide, or else that cell could no longer function the way that it normally would. So we're going to talk about the limit for cell size. And to do this, we have to do a little bit of math. Now, we're going to assume that a cell is a cube shape. So, like one of my weirdo Rubik's cubes. Right? The reason why we want the cell to be a cube instead of a sphere like it really would be is because the math for surface area and volume on a cube is much, much easier than the math for surface area and volume with a sphere. Because in order to get the surface area, you have to use that pi factor, right? And multiplying by pi always makes things ugly. So instead of doing numbers and math to have messy things that you need a calculator for, we're just going to assume that the cell is a cube. That way, it's easy math. What's the surface area for a cube? How would you figure out the area of one side of the cube?
Length times width.
Length times width. And then how many sides are there?
Times 6.
So you just multiply by 6. So that's easy. The volume of the cube is also very easy because all the sides are the same. So what do?
Length times width times height.
Length times width times height. And it's easy. You can do it in your head. The math just makes it a lot easier this way. So we're going to talk about surface area to volume ratio. We're going to actually use some math to define what makes that surface area to volume big versus small. Right? You have a table in your notes that you're looking at, but I'm just going to draw it up here as we go. So it has diameter here, right? And then it's going to have surface area and volume, and then a surface area to volume ratio. Oops. Goof that up a little bit. Surface area to volume ratio right there. And so we're just filling in as we go, right? But you can help me do the math because it's simple math. Remember, if I'm doing surface area, it's length times width times 6. And then volume is length times width times height. Since it's a cube, the length, the width, the height are all the exact same value. So we just start with a number. Easiest number to start with is 1. Right? If the diameter is 1 generic unit, we're not actually using units here. We'd probably use something like a micrometer or a nanometer when we're talking about a cell that's so small you can't even see it. But the diameter is 1. So then I have to calculate a surface area, which would be length times width times 6, right? So what's 1 times 1 times 6?
6.
That was pretty easy, right? And I also need a volume. What's 1 times 1 times 1?
1.
That's pretty easy too. So again, we're only assuming it's a cube because it just makes the math so much easier that we don't have to worry about it as much. But our surface area to volume ratio then is a 6 to 1. All right, sometimes you write ratios this way. Sometimes you write them as a fraction, but either way they would need to be reduced. This is already reduced, so it should be fine. So then we think about a bigger cell. Let's say the diameter is twice as big. So I'm going to make the diameter 2. Now we have to calculate again, what would be the surface area of that cube?
24.
So 2 times 2 is 4 times 4, 24. That sounds right. Everybody agree with that? 24? And then volume would be 2 times 2 times 2.
8.
So then I need a ratio. But again, you do actually want to reduce that ratio. Can you reduce a 24 to 8?
Yeah. 3 to 1.
Turns into 3 to 1. Good. And then you can see from there, if I double the diameter, right, does the surface area to volume get bigger or smaller? Does that surface area to volume ratio get bigger or smaller? It got smaller. Half as small as it was before, right? Instead of being 6 to 1, it's 3 to 1. So surface area to volume shrinks as the cell gets bigger. So I could do one more just to model it even further. Let's say I have it 3 times bigger than the original. The diameter is 3 generic units, whatever it is. What's that make my surface area? Excuse me.
54, because 3 times 3
Yep.
times 6 is
54. Sounds right. 9 times 6 is definitely 54. And then the volume is
27.
27. And that ratio can be reduced to
63, so
2-1.
2 to 1. So again, as you get bigger, I could keep going with this, but then the math gets a little bit harder then. But I can keep making this cell get bigger and bigger and bigger, but that surface area to volume ratio keeps getting smaller and smaller and smaller. Now what we need to understand is why that would matter. Because there gets to a point where the surface area to volume ratio is too small for a cell to function. But why are we even worried about a surface area to volume ratio? So I'm going to draw another thing in here. I need a new page so that I can do it on the board for real. Page after current should be fine. So this is my actual cell. I'm going back to a spherical shape, but the surface area of this sphere is just the outside surface. What is surrounding on the outside of a cell?
Membrane.
The membrane. So when I'm talking about the surface area, I'm not actually talking about a surface area, I'm talking about the membrane itself. Right? How big is that membrane that's surrounding the cell? So the surface area is your membrane, the cell membrane. Whereas the volume is the fluid that fills that cell. What's that called? Good one. What's that called? The volume. The fluid that fills the cell. You know what it's called. Starts with a C.
Cytoplasm.
Cytoplasm. So the volume is your cytoplasm. And then what you have to understand is that you kind of relate this to an idea of supply and demand. Where do you need things in your cell, right? Your cytoplasm is inside the cell. You need certain things inside the cell, right? But the only way things can get into the cell is through what? Through the membrane. So if the membrane is really, really small,
they can't get
you can't get as much through. If the membrane is really, really big, more could get through. So it would seem like maybe a really, really big membrane would be a great thing, because if I had a small door over here, I can bring in one desk at a time. If I had a much bigger garage door opening, I could bring all of the furniture basically at the same time into this room, and it'd be pretty easy to do that, right? But at the same time, when you get a bigger cell, the membrane's not the only thing that's growing. The volume's also growing. And the volume grows faster than the surface area because it's cubed and not squared, right? So this number was getting bigger. This number was also getting bigger, but this number was getting bigger faster. The volume was getting bigger faster. You see what I'm talking about? And that's why this surface area to ratio volume is getting smaller and smaller and smaller. But if the volume's getting bigger, that means that your needs are bigger, right? So, yes, as a cell gets bigger, seemingly your supply can get bigger. I think supply has 2 P's, but I spell things wrong a lot. So seemingly that supply could get bigger with the bigger cell, but you also have to understand that you have a certain demand in that cytoplasm, and that demand is increasing faster than the membrane is. Right? The volume is increasing faster than the surface area, so the supply might get bigger with the bigger cell, but the demand gets even bigger than the supply eventually. So it's an issue of supply and demand. You need things in your cell. They have to go through the membrane to get into that cell. So you have a supply, you have a demand. The reason why you want a big surface area to volume ratio is because that would make your supply big enough to meet your demand, right? Excuse me. Let's draw that arrow the other way, actually. So we'd have a relatively high supply to meet a relatively low demand. Does that make sense? Because when the cell gets bigger, although the supply does actually increase, the demand increases faster. So eventually you get to a point where you don't have a big enough supply to meet a really big demand, which is bad, obviously. So you want one of these to be big and one of these to be small. It's better to have a high supply to meet a relatively low demand than the other way around. Because if the supply is too low to meet that demand, that cell can't function. It won't have all the things that it needs to survive. Is that clear to everybody? Does that make sense? Because it's a very basic concept, but you just have to understand that even though both of these things increase, the supply and the demand, as the volume gets bigger, one of them increases faster than the other. So we're really worried about how fast that demand is increasing. It increases faster than the supply. So if you have a big cell, if it was big enough for you to see it, if it was the size of a basketball, it would need way too much stuff inside of it for that supply to keep up coming from the outside. So there's no way that that could function appropriately. As you can tell, because you've never seen a cell, they have to be very, very small in order for that supply to be big enough to meet the demand. Right? And you just know that by logic because you've never actually seen a cell big enough that you didn't need to use a microscope to view it. So you know that that cell size is limited, but why is it limited? It's because the supply has to meet the demand. Is that cool for everybody? So it's this idea, but it's also one more thing that may or may not be simpler. It's just kind of weird. So you got another model here. I don't know why I use red there, but it doesn't really matter. So I got this cell, and I have something from last chapter. I have a pyruvate over here. Where are those supposed to go in order to get the rest of the energy out of them? Nope. They stay in the cell, but they have to go into a certain organelle before you can do anything with them. You got to move them into the mitochondria. So let's say the mitochondria is over here. And before you can get anything to happen, this pyruvate has to get into that mitochondria. Right? The pyruvate's on one side of the cell, the mitochondria is on the other side of the cell. If this was a big cell, would that make it take longer or a shorter time for that pyruvate to get from point A to point B? A lot longer, right? Depending on how big the cell is. If the cell's really, really tiny, then point A and point B are really, really close together. And they can get to each other a lot faster that way. Does that make sense? Yeah, you can draw this too. It's another idea that is definitely important here. But the other thing with this, do you have a question?
Yeah. So if it was really smaller, wouldn't everything be more cramped up?
But you do understand that these things that we're talking about are super tiny themselves. Like the pyruvate is like 1/1,000,000th the size of the actual cell, even though the cell is really, really tiny to you. The pyruvate's even smaller, so that's not really an issue. It's basically like our classroom, right? Maybe I'm a mitochondria. That's about how big one would be, and then like a piece of lead would be a pyruvate. So you need to get that thing to move around this classroom. This classroom's still really big compared to that pyruvate, right? But if you made the classroom the size of the gym, that just makes it that much harder for that pyruvate to get to the mitochondria. It's just that much bigger. That makes sense? Relative sizes. But you also have to remember from before, how do things move in the cell? Is it going to move straight from A to B, like it knew where it was going? How's it going to move? It's going to move randomly. So if I had Calvin stand up right now, and you're going to try to get from where you're standing to that computer card over there, even if you wanted to go in a straight line, you couldn't, right?
I
But you're supposed to be moving randomly. So you just walk in a straight line, you run into something, and you turn because you bounced off of it, and you go the other way, right? If we're just waiting for Calvin to plinko over to that computer cart, it might take a little bit. And obviously this is a pointless task at a certain point, to a certain extent, so you might want to just sit down again. It would take a while for that to actually work. But you got to remember that these things don't move in a direct line. They're actually just kind of wandering their way around in random directions, running into things and bouncing around.
Oh, wow.
Maybe it eventually gets to B, but it's not going to move straight towards B. So the closer B is to A, the more likely it is to get there, ever, right? If it's got to bounce around a huge cell before it can get from point A to point B, it might never make it there, or at least not fast enough for you to be able to do the reactions to stay alive that you need to occur in a timely manner. So we're counting on diffusion to move these things as well. So you can't just have this huge space for them to move through. Not unless they had a brain of their own and they could go straight from A to B. But since they move around randomly, it doesn't really work that way. It needs to be really close together, or else that's never going to happen. Right? So again, that's just a different way to explain it, but that's almost a more complicated way to explain it. Because even if you did have that thing inside the cell, it still needs to go where it's supposed to go, and you have to rely on random motion to get it there. But this other problem, right, we need a big enough supply to meet the demand. That one is a little bit easier to follow along with once you understand that the surface area is the membrane and the volume is the cytoplasm. So those are the concepts that we're trying to deal with. There are a couple questions on here, but I'm just going to make 7th period answer those on Monday. So if you can quit the recording, we'll answer them. But we don't need to keep recording here.